Okay, so let's look at this example of integration by parts. We're going to evaluate the integral of x e to the x dx, and hopefully at some point you've learned that this integral can't be evaluated by elementary means. By that I mean it's not, I can't think of a function off the top of my head easily whose derivative comes out to be x e to the x, but I'd still like to take the antiderivative of it. So we're going to go ahead and use the technique of integration by parts. When you have a function whose derivative never zeroes out but sort of repeats itself over and over again, like e to the x or sine of x or cosine of x or cosh x, and then you have a polynomial function, in choosing which integral or which factor to be how we denoted by u in the integration by parts formula versus v, typically the rule of thumb, although it's just a rule of thumb, is to let u be the polynomial, because with every du that shows up underneath the new integral sign, this expression becomes easier and easier to evaluate. And if you have a function that continues to cycle through derivatives, we usually let that be our dv. Again, that's just a rough rule of thumb. So here we go, let's give it a shot. In this case, we'd say let's let u equal x, which would mean that du is equal to 1 dx. I sometimes have students forget this dx here. It is essential that you have that. And then we'll let dv be the expression e to the x dx. Again, sometimes students forget this dx expression here in the integration by parts formula. And you really do need it because it's going to be a true substitution. In place of e to the x dx, we're going to think of it as the expression dv. And then by integrating this, well, this is easily integrated, and we end up with v is equal to just e to the x. So now all we have to do is follow the integration by parts formula that says the integral of u dv is equal to u times v minus the integral of v du that we derived in the previous video. And so now we have the integral of x e to the x dx. Why, that's equal to the product of u and v. So there's u is being played by x in this problem, and v is being played by e to the x. So this gives us x e to the x minus the integral of v, which is e to the x, times du, which, just to be pedantic, I'll write as 1 du. And the whole idea is, behind integration by parts, is that we took this expression that was maybe hard to find an antiderivative for, and in this case, and this isn't always the case, integration by parts is just a tool, but in this case, the expression that showed up in its in the integral of v du is an easier expression to find an antiderivative of, and so that was a good choice. So we end up with x e to the x, just finishing this out, minus the integral of e to the x. And I'm sorry, I made a mistake here. Folks, I wrote du. That should have been a dx, so you can correct me. Dx. And so all I did there was simplify the 1, but the point now it's even clearer that this new integrand is easier to find an antiderivative of than was the original. So we end up with x e to the x, and then we know the antiderivative of e to the x is e to the x, so we get minus e to the x plus c. Remember, we're finding a general antiderivative here, so we need a family of functions, so we often will have that arbitrary constant. Hopefully that answers any questions on that example.